So I took this doubling every year and extrapolated it 10 years from 1965 to 1975 from 60 components to 60,000 components on a chip.
First thing you have to tell him is, guys, we've been giving you a free ride for 30 years while you write your crummy software and we made it faster. Right? That's over.
The future is parallel. Single cores are not getting any faster.
Thanks for coming to the lab lecture. So today we are going to give you a preview or say an overview on lab 3. So as you might have an idea now is that after lab 2 we are gradually building a processor that supports MIP instructions, MIP's a subset of instruction set architecture. And in the previous lab, in lab 2, you are we only require you to build data path components, and if you want to verify if the correctness of your data path components, you have to write your own test bench, and you have to design your own test cases to see if they really fly out. Right, so that was the lab 2. However, for lab 3, we are starting to have a feeling that this is going to be a working processor in a way that the main goal of lab 3 is that you are going to add a control unit on top of the data path in the previous lab. And after you have those control units, your processor will support instructions including load word, store word, add immediate, subtraction, and, or, not, and exclusive or. However, the only other types instructions that we haven't supported are branch, jumps, and those will be your responsibility in lab 4. But for lab 3, we want to support quite a few instructions that doesn't have branch, but doesn't include branches. So this is the goal of lab 3. So remember, this is what you guys had in lab 2. So this is what you guys had in lab 2, right? You have this data path, and if you have some memory, you probably also have done a processor.b module that covers the whole thing, right? But right now in lab 2, what's the difference between lab 2 and lab 3, right? So compare this two. Did you see that? So your data path components, they will maintain the same layout. They will not be changed. The only thing that you need to do in lab 3 is adding these red parts on top of your data path. So that's why we said so some of you asking like, okay, if I have done lab 5, can I get an A or something? That's not possible, because if you have done lab 5, it must be building on top of the success of your lab 2, lab 3, and lab 4. So the data path in lab 2, right? If you don't have it right, there's no way you can get the lab 3 working, right? So that's the thing. Right, so compare with that, right? So you already have the mux, you have the mux input. We already gave you the LOU. We already gave you the data memory module. So everything you need to do now is to connect the floating signals that you have in the previous design with the inputs, with the outputs from the control unit as your input. So to get the output from your control unit, how do I know what type of output that I should do for each instruction is that you have to look at the opcode from each instruction to determine what type of instruction is, what the operation that instruction requires to do. And for arithmetic operations, we specifically have another function code that's encoded in 5 to 0 bits. So for arithmetic instructions, they all share the same opcode, that is 0. However, their function codes are different. So to make sure that your like instructions using the LU correctly, you have to set the function code according to what's encoded in 5ths to 0s position in your instruction. So let's look at this, right? So if I have a load instruction, right? For example, if you have a load instruction, you know that you should enable the read, and you know that you should make the memory to reg to be 1 as your input for write back, right? And you know that your destination register should be encoded in this way. So you have to set this max to 0. So you might have a question like, okay, how do I know what to do, right? So theoretically, if you know what each instruction is doing, you don't necessarily need to lay out your circuit like what I'm doing here. But if you are lazy, saying that you are a lazy guy, but you really like to follow the standard as what I published here, here's the table that I made to save your time. So this is the list of instructions that you have to support in your control unit. So look at the list. There are load to so there's a huge set of instructions like the load store instruction. There are I-type instruction. They have different opcodes. So if you see, so those are the inputs. So these are the inputs. If you see this and the type is not in the input. So these two, they are the inputs, right? So if you see the opcode is this two, you know they are either load or store. And the function in should be set as this. And the store word instruction, that's the only instruction that doesn't produce an output. So we don't need a reg destination because we don't care, as long as you make sure that the register write is turned off. So some of you, so that's actually one design, one small design bug that a lot of previous students have, is that they forget a store word instruction is an instruction that doesn't write to a register, and they just thought that everything here should be 1, but it's true that everything here should be 1 except for 1. The store word instruction, the register write should be 0. And memory low word instruction is the only instruction that will read memory. So other than the low word instruction, everyone else memory read should be set to 0. And store word instruction is the only one that would write memory. So other than the store word instruction, other instructions, you have to set the memory write to 0. And low word instruction is the only one would use the output from the memory to register as during the write back staging. And as we said, store word instruction doesn't update register. So as long as you set the register write to 0, it doesn't matter like what values you give to the mux. Other than that, everyone should be 0. And because right now we haven't supported jump and branch, so everyone's jump should be 0. But you might want to ask, okay, why do I have this? Because later on you are going to use this, right? So that's why we have this column here. And for, as I mentioned, right, if you have arithmetic instructions like add, sub, or whatever, their opcode are all 0. You have to tell from their function code to make your LU function correctly. And so as you can see, right, like a different function code, we have different outputs, right, to the function in for your LU. So that's the stuff that you have to be paying spatial attention to. All right, so this is so this lab is actually just wanting to implement like, what do you guys want to say, like some kind of, like combinational logic that would output these control signals. So you just make a table, you just make quite a few case or if else statement, as some of you already asked on the Piazza, right? Then it should not be a very difficult lab. And however, because we are now supporting some real instructions, so we will provide the following benchmark programs that you can download from the website to test your benchmarks, to test your processor is working or not. So here, right, like I said, instead of designing your test cases, we are using real programs to test your processor. And so here's the test bench. So this program is called No Branch Hello World. So for this No Branch Hello World, its assembly code is like this. So you add immediate and then you subtract the value with 0. Well, you subtract the value with 0 and put it to 20. So this is basically doing a move from 10 to 20. And then you do subtraction, you do subtraction, you do subtraction. And the reason why we get this address is because later on, well, so you will see that if your processor functions correctly, you will see some output on your model sync console. And the reason why we can do that is because we use memory mapped I/O for this processor. And the memory mapped I/O means that we map the console output to a specific address in our data memory module. So you don't have to deal with that part because our data memory module already deal with that with you. But to print the right thing, all you need to do is make sure that when you perform the store instruction, you do give the store instruction the right input. So for this output, we use ASCII coding. So if you are familiar with ASCII code, you know that the hex in 40A actually represent H. So if you put 40A in H, then store it to the memory address that correspond to the console output. That's how you see an H on the screen. And it's probably not too difficult for you to imagine what the rest of the code is about. So because this is the first time that you have a processor and you want to you probably are not so familiar with what's going on. So if you really want to debug your processor, sometimes you do want to compare the register value and the waveform that you get. So there is a simulator in Windows under Windows called Qt Spin. So the Qt Spin for the Qt Spin we also include a No Branch Hello World .spin.s for you to simulate regarding what's going on in your code. So the good thing about this is that you can just do a step-by-step simulation, and then it will print the stuff on a console for you. So let's say like, okay, right now that's stop, and then so there are some beginning status you have to set. For example, so first of all, let's clear all registers, and that's and the settings part. Well, because for MIPS instruction set architecture, we do want well, so that's that. Okay, so display symbol, initialize simulator. Okay, so for the simulator, right? Because for MIPS instruction set architecture, we support we suppose your code should start with this address, and that's why our PC asks you to start with this address. And some of you mentioned there is a web-based MIF simulator. However, I just checked that one. Its PC doesn't start with 004000000. So in that case, you have to map the PC to your with an offset, and sometimes it won't give you the right result because thinking about if you have jump instruction, that's going to be wrong, right? So that's definitely not a, so if you just want to figure out like what instruction is doing, that kind of simulator is probably okay. But for those web-based simulator, it won't work for the lab for the reason as I just mentioned, because it doesn't set the PC correctly. Okay, so so as you can see, right now I'm using a single step. So after I executed the first instruction, the PC right now will become 40004. And because the first instruction tried to put 0x4000 into 10. So you can see register number 10, which is corresponding to T2 right now, contains the hex value of 16K, right? And if you keep iterating, you will see like R20 is changing its value gradually. And then at this point, we got an H we got a 48 as the input for the store word, and then you can proceed, right? And for here, you see an 65 there. So you can check your register values with the simulator to see if you really get your implementation right. So this is a simulator that you might be able to leverage for your lab 3. All right. So so this is the spin simulator. Okay. So here, like in lab 2, I don't know how many of you have done the lab 2 interview, but if you have done the lab interview, you know that our tutors are going to ask you quite a few questions. And if you interview with me, I will ask you quite a few questions as well. And the reason why we ask you guys to do interviews instead of writing reports for quite a few reasons. So first of all, for written reports, it takes your time, and it also takes our time to read it. And the ironic thing is that although we suggest you guys to perform the reports individually as a group, but all the reports that we have received in the past, they are surprisingly similar. So it makes no sense to have you guys duplicate other groups' reports. And so we just do interviews instead. And during the interviews, we will randomly ask quite a few questions so that we know if you really do it by yourself. So if you didn't do your lab by yourself, it's easier to identify from interviews. And for the interview this time, we are going to ask you to simulate no branch hollow world for at least 1 microsecond and show us the waveform, explain why the waveform looks like this and why this waveform tells us that your processor is working correctly. And then simulate for 5 microseconds and show us the schematics, explain why there's such a unit in your design and why does that make sense. And finally, get the maximum frequency out of it. So these are the 5 things plus some random question that we have in mind that will be in your interviews. Okay, other than that, I think that's everything I want to talk about in this lab. Any specific question? All right. If not, I will see you guys in the office hours on another day or the lecture later on. Have a great, wonderful rest of your day. Floating high into the darkness. I hope I get there soon. It's so many